All right, let's get right into it. Today, we're taking on what might just be the single biggest puzzle in all of science. We're talking about a massive disagreement between our two best theories of how the universe works, and a brand new, kind of radical idea that might finally fix everything. So let's explore the biggest mistake ever made in physics. So let me just start with a question for you. What do you think is the single worst, most spectacularly wrong prediction in the entire history of physics? I'm not talking about being off by a little bit. I mean, just wildly, almost laughably incorrect. Well, the answer leads us to a number so completely absurd, it honestly looks like a typo. There it is, a 1 with 120 zeros after it. This number, this is the size of the error. It's the massive gulf between what our most fundamental theories predict about the energy of empty space and what we actually go out and measure. And to be crystal clear, this isn't a small whoops. This is like trying to measure the width of your hand and being off by the diameter of the Milky Way galaxy. It is just wrong on a cosmic scale. This colossal failure has a name: the cosmological constant problem. And it really is physics' biggest blunder. It all comes down to a fundamental clash between two worlds: the world of the incredibly tiny and the world of the unbelievably big. Okay, so here's the heart of the issue. Our theory for the small stuff, quantum field theory, which is insanely successful, by the way, it predicts that so-called empty space should be absolutely fizzing and bubbling with a ridiculous amount of energy. But then our theory for gravity, general relativity, looks out at the whole universe and sees, well, almost nothing. Just a tiny, tiny amount of energy that's gently pushing the universe apart. The two pictures just do not get along. At all. You know, for decades, this problem has had the smartest people on the planet completely stumped. But what if we've been looking at it all wrong? What if the problem isn't really with the energy, but with our idea of space and time itself? A wild new idea suggests that to solve this mystery, we have to rethink the very stage on which the universe performs. So the standard way of thinking is that space-time is just there. It's the boring, passive background. But a new framework called CRET, that's short for Constraint-Resonance Emergence Theory, it says something pretty mind-blowing. It says space-time isn't fundamental at all. It actually emerges from something deeper, kind of like how a smooth, continuous image on your screen emerges from a bunch of tiny individual pixels. And the consequence of this is just huge. If space-time emerges, it can act as a kind of buffer. All that crazy, high-energy fizzing from the quantum world doesn't have to directly translate into the gravity that shapes the cosmos. This quote basically says we can finally separate the two. We can get in between them and cut the problem off at the source. Okay, so how does this new picture of space-time actually solve that insane 10 to the 120th power problem? Well, CRED comes with a toolkit. It has 3 specific tricks up its sleeve. Let's call them cosmic levers that could finally close that massive gap between what we predict and what we see. So here's CRED's 3-step plan. First, it changes how we think about the constant, making it a property of the whole system. Second, it finds a way to hide most of that wild vacuum energy from gravity. And third, it lets the little bit that's left over change slowly over time. Let's break down how each of these levers actually works. The first lever is a really big shift in thinking. So instead of the cosmological constant being the sum of every little bit of energy in every nook and cranny of the universe, CRIT says it's more like a single global setting for the entire cosmos. Think of it like a master thermostat. It's set by the overall network of the universe, not by all the chaotic little quantum hotspots. The second lever is a concept called sequestering. And honestly, the best way to think about it is like a company's budget. You might have billions of dollars flying back and forth between different departments. That's like the huge vacuum energy fluctuations. But gravity, well, gravity is like the CEO. It doesn't care about all that internal noise. It just looks at the final tiny net profit on the quarterly report. Most of the vacuum energy gets hidden away or sequestered. And the third lever adds a little bit of flexibility. That tiny bit of vacuum energy that gravity can see, it isn't perfectly fixed. The idea is that as the universe expands and the underlying structure changes, this value can gently evolve or run, changing very, very slowly over billions of years. This helps the theory perfectly match the universe we observe today. Now look, having a clever story is one thing, but for a new idea to be a real scientific theory, it has to pass some serious tests. The big one is it absolutely cannot break the known laws of physics. So the all-important question is, does this new emergent gravity still act like the gravity we know and love from Einstein? And this right here is the biggest test of all, the equivalence principle. This is basically the iron law of gravity. It's the rule that says everything, a feather, a bowling ball, a beam of light, they all have to feel gravity in the exact same way. Any new theory that messes this up is, frankly, dead on arrival. So how does CRIT do? Well, the answer is a resounding yes, it passes, and it does so for some really deep reasons. The theory is basically built from the ground up to respect some fundamental properties of gravity that force this universal coupling to happen. And of course, it also respects the incredibly precise experiments we've already done that confirm this principle. So, long story short, CRT is designed to play by Einstein's rules. There's another huge check it has to pass. Is the solution stable? Or does all that quantum weirdness that caused the problem in the first place just sneak back in and ruin the solution? And again, the answer seems to be no. The mechanisms that CRIT uses are protected from these kinds of quantum effects. Physicists have a term for this. They say the solution is radiatively stable. It holds together. Okay, so we've got a really elegant new theory. It solves a problem that's been around for a century, and it passes our most fundamental reality checks. So, what now? Well, this is the best part. A real scientific theory makes predictions you can actually go out and test. The hunt for evidence is officially on. So here is what astronomers and cosmologists are actually looking for. Because CRIT's vacuum energy can run a little, it predicts that the expansion of the universe might not be perfectly constant over its history. It also predicts that the way galaxies and galaxy clusters clump together might be a little different than we thought, and it might even have left some tiny faint smudges on the afterglow of the Big Bang. These are really subtle signals, but they are things our best telescopes are searching for as we speak. At the end of the day, CRIT gives us a compelling, testable, and really profound new way to look at physics' biggest blunder. It suggests that what we call space-time isn't the fundamental floor of reality, but this incredible, emerging tapestry. Which leaves us with one last, really tantalizing thought. Could it be that the very fabric of our cosmos is woven from the most basic thing imaginable, pure information?